Hello. Uh, in this session, we will mainly talk about the fork system call. The fork system call is one of the most important functions in Unix or Linux-like operating systems. It is used to create a new process by duplicating the calling process. The newly created process is called a child process, while the process that calls fork is the parent process. So if we want, say, to know more details about fork, one can write man to fork. Okay, so this is the detail. These are the details about the fork system call. Now there are three important key concepts here, like which are involved in this whole stuff. Like process, as we know, it is a program in execution, contains an address space, program counter, stack, heap, and other resources. Now other concept is called as parent process. The process which invokes the fork system call to create a new child process is called as parent process. Whereas the child process is the new process that is created as a result of the fork system call. It is a duplicate of the parent process, except that it has unique PID or process ID. Now how it works? So to create a child process, we do give or use a fork system call. Okay. Now, when a process calls this fork, like one can see here, which is shown in front of the details of the fork system call, the operating system creates a new child or a process by duplicating the current parent process. So it is exact memory copy, okay, exact copy of the parent, which includes memory content, file descriptors, environment, stack, etc. Modern operating systems make use of a technique called as copy on write. This means that operating system does not immediately duplicate the entire memory space. Instead, it marks the memory space as read-only for both parent and child. If either process writes to the memory, a copy of that page is created by making sure that the process remain independent of each other after a write is completed. The parent process gets PID of a child process as a return value of the fork system call or fork call, whereas the child gets 0 as a return value of fork. After successful execution of fork, both parent and child processes continue execution from the point where the fork was called. The parent and child may execute the same code, as we know the memory space is copied, but their execution is independent. Now, this is why it is common to make use of if-else logic to distinguish between parent and the child based on the return value of the fork. Now, as I stated, the parent process receives a PID of the child, which is a positive integer greater than 0, and the child process receives 0. Now, what happens? Suppose if fork fails, now reason may be different. It returns -1 to the parent and no child process is created. Now, as one can see, syntax is like this. You can make use of system call fork over here. Okay. Now, when the system call is copied or when the system call is given, now suppose like when I said that it may fail, there might be different reasons of failure. It may fail due to say system resource exhaustion. If all resources are exhausted, then the system, when it runs out of resources such as memory or process limits, it may return an error. But it can happen again, like if the operating system hits a limit of number of processes, a user can create a error may be thrown or your fork system call may fail. Even if there is not enough memory to create a duplicate of the child process parent process, then ultimately again it may fail. Now, when a process calls fork, the operating system adds the child process into its parent process table. The child process will have now its own PID and also will get information about its parent PID, PPID, which can be accessed by different system calls, which would be seeing afterwards get PID and get PPID. Now let us see an example where we will introduce or understand how to make use of a fork system call. So let me write say emacs fork.c. So we will make an habit of writing or including these header files like include unistd.h. I will be using printf and scanf statements here to introduce you this fork system call. So that's why I will include std.h as well. So it is always better to include stdlib.h, though we may not use it, but like as we are going to make use of same code later stages, so we'll include that file too. So let me include now main function. Now, as we know that fork system call is not going to take say any parameter, but still like I will take a variable which will hold the values written by the fork system call. So let me write PID underscore T, which is a standard structure used for processes. Okay, and I will declare a variable PID over here. Fine. Now let me write PID is equal to fork. I will include printf value returned by fork stored in PID is say %d/n, and I will display this PID. Okay, so we'll add simply /n both the places, and I will simply write return 0. Now let us try to see what this code displays. Let us save this code. Let us compile gcc fork.c -m32. I want a 32-bit file created. So I'm just having or using another terminal as well here. We'll require it after a while. So let me execute this code. Now you may see value returned by fork stored in PID is 8144 and value returned by fork stored in PID is 0. Now we don't have any mechanism to really see whether both the processes got created or not. Though the output is shown twice. As I stated earlier, whole code is copied as it is in both the child, both the parent as well as the child. Same, they would be executing same code, but instance of execution would have a different value. Say for example, with parent, it would be holding PID of a child, and within child, it will have a value 0, which is the value of the exact return value by the fork system call. Correct, after successful execution. Fine. Now let me add one simple scanf statement there so as to see what exactly is happening. Okay, so it should execute both the statements and it should call or read values using a scanf. So max fork. Now simply let me declare a variable integer a. Now if I say scanf %d %a, let us save this code. This is the just code we have written. We are adding a scanf statement. Let us hope there would not be any error. Okay, now let us execute this. Now you may see it is waiting because we added a scanf code. Now it should ask for us two values. Now if I wish to see whether these processes are running or not, so let me write ps-a, okay, grep a.out to only see the instances of a.out. One can see here two values, two services are running. So you can check 8233 and 8234. So in this case, like if we say that this is the value printed by the parent, which holds PID of a child, correct? So 8234, this way would be a child, correct? It is a child. And probably this is a code that is executed in a child process, which is holding 0 now as a fork system call return 0 in child process. So now if I use say EJ capital H to display the tree. You can see the tree now, the tree kind of structure, tree-like structure. So one can see here, this is parent and this is child. There is a hierarchy added here while displaying this process tree by the code. Now suppose if I give input here, say 4. Okay, let me check both the process are running. Now when I press enter, now this parent process is gone. So it completed the execution. Now it is not shown here, correct? You can see here 8, 2, 3, 4 is remaining. Now if I write here 6, so I press 6 rather here. And if I try to check now output, now you may see it is vanished. So if I write ls, that means the value which was read by me, which was given by me to the standard input is not displayed there the way that I saw that 4 is displayed here. Okay, we'll talk about the reasons why it is not displaying that after a while. Let us make small modification in the code again. So let me open that file and let me add to see what value was inputted by me for this print, scanf or for A. Okay, value of A is %d and let us display this. Fine. So we'll add here /n. Okay. Let us save this. I will add a /n afterwards to only see the output. Now let me again compile the code, link together. It generates a.out. I can see now EJH again. You can see 8315, 8316. So child in this case is 8316. So you can see value returned by fork stored in PID is 8316 and value returned by fork stored in PID is 0. So this may be a code. This code is executed by the child process and this output is shown by this parent process. Let me input now say 56. So I inputted 56. So you can see that value displayed is value of A is 56. If I display this, now parent process is gone. Correct? Now is the child process memory? Probably yes. So I'm inputting 67 there. So what it took? It only took 6 and 7 is added there when I press 67 together. Now you can see it is showing me 7 as not understood as in a command not found. And it is removed. Now we'll understand after a while why exactly it is not taking this input. Okay. First of all, let us go back and try to see differently. Now we are not sure this value of A is executed by parent and value of A is 6 is executed by a child. It is very difficult. Though we could see here that when it displayed value of A is 56, it removed parent from memory. That means this 56 was from parent, correct? And the 6 is now from child. So we'll write a clear code now by adding if else the way that I stated earlier. Let us make the changes in the code again. Okay, now what I'm doing is, as we know that fork returns 0. So I'm writing if PID is equal to 0. Now this would be where in a child value returned by fork stored in child PID. And like we'll write this here. Okay, we'll read scanf. We'll use printf and value of A in PID. So we'll use PID %d is %d. So I will display PID and A value. So this is now if part. So let me add else part 2. Now if it is not 0, which is a non-zero value, which would be always in a parent process, we'll write here parent PID is value returned by fork in parent. Now this is the value returned here, stored in child value of fork We'll reorganize this value of forks return value, returned value of fork store in child is %d. Okay, so we'll not add this. Okay, and value returned, uh, value returned. So I'm making some modifications so as to get good text. Returned value of fork stored in parent. Now I will not write this PID. Is %d / n. We'll write PID here. Fine. And we'll write the same thing. Fine. Like we'll have everything other than this as same. So let me write else here. Fine. Let us save this code. Let us go back and now compile again. Now let us execute this. Now you can see return value of fork stored in parent is 8426. So you can see both of them parallelly executed. Return value of fork stored in child is 0. Correct. Now one can check here. Both the processes are running. So 8426 is the child. Correct. And 8425 is a parent. Let me add here again 4. Value of A in PID 8426 is 4. Correct, because now it is not a PID. Actually, it is a PID value stored in a child, stored in a parent. That's why it is showing this value of A in PID 8426. Actually, it is not value from 8426 because we wrote PID there. That's why it is displaying. So if I write here other value, it shows value of A in PID 0. So we know that 0 is not a PID. So this is actually a return value. Okay. So if let us check the code again and we'll write here value of A, okay, in parent with value of A in child with return value of PID. Okay, value of A in parent with return value of PID. Correct. Now this would be clear. Let us save this code. Let us compile. Let us execute. Now if I write 5, value of A in parent with return value of PID 8494. If I check this is the child because parent already executed. Now I'm giving other value. Now it is displaying this. Correct. Now both of the processes are gone. I can display the remaining. Now you may see like when I inputted a value, it actually took my ls command because this bash was added prior than this the child process because child process was sent in background. How do you check this? So let us start again the execution. Now here what I will do is instead of EJH, I will use AUX. Now you can see here like both of the processes are having plus as a sign with sleep to be the state. So if I write man PS, let us see what is plus. If we go below, then we would be getting information about that S and plus. Yeah, here. So S means it is in interruptible sleep waiting for an event to complete because it is waiting for our scanf. Correct? That's why both of them are having S. And what is plus? Plus is the foreground process. It is a foreground process. That's what it is saying. Now, when we listed this output, we can see that both of them are with S plus. Now, if I add a value here, 5, okay. Now, after I input value 5, when I press enter, we'll try to see what is the state, which currently for both of them is S plus. Parent would be removed. 8544 would be removed from memory. Now 8545 would be running in memory. Correct? Let us check. So I inputted 5. Okay. Now if I check this output, check what happened. Now when I inputted a value 5, you can see value of A in child with return value of PID 0 is 5. That means it now executed a child process and it is waiting for this. Now as child finished execution, as child finished his execution because it displayed the value and now it is waiting for the parent process, and that's why it enters it into Z plus mode. And that this Z is a zombie process and which is a foreground process. It is still in memory, and that's why it is not in doing anything, and that's why it shows it as a dot out in square bracket with defunct mode. Okay, would we get talking about this Z plus or a zombie state after a while? Okay, now let me input here a value 8, say, and let me press enter. Now you may see like the order earlier, what are the earlier thing that we saw? Earlier it was executing parent process and it parent was removing out. Now we see in the same scenario, we are seeing that child was given a chance, and this was decided by the operating system through a program called program process scheduler, which decided that child should be given the chance here. So you may see sometime a parent process is given a chance, or sometime you may see a child process given a chance. So let me execute again. So that we will be seeing that. Okay, now again, let me check this output. Both of them are here. 8626 is the child process and both of them in S plus mode. Now I am giving 67 as an input. Now you may see this is the best example that we are seeing currently now. Parent is removed. Parent is gone. Now child is there. Now you can see that now which program is in front. So we see that there is a shell program displayed. That's why it is showing you a shell prompt. And your a dot out enter into S mode. That means it that as plus is not there, ultimately your process is entered into a background mode now. And it is waiting for my input. So that's why when I press 7 here, it is not showing me that 7 there because it is running in background. And now whatever I type would be a command for shell. Correct? And this is how the process may get terminated. And this is how, like you can see here, what are the example that we saw. In most of the cases, our parent got the priority to execute. We saw again another example where child was given a chance to execute. So this may be decided by the program, the process manager. So again, let us try what happens. 8656 is a child. Now I am giving 89. Again, parent was given a chance. That's why child is remaining. Okay. I inputted 87. So it showed 8 there and 7. It is taking as command line on the shell as a command name. Correct? And this is how the fork works. And we will be talking more in more detail about process scheduler later. Like the way that we saw different functioning mechanism, like what was happening when we executed a dot out. So at one point it showed like parent is executing. At one point it showed child was given a chance to execute, whereas the parent process was executed later. Now when child was given a chance, child completed execution, the child process entered into a defunct mode, that is zombie state. Okay. Thank you.